Module 10, Chapter 7.5, Determinants and Kramer's Rule. Recall, a matrix is a rectangular array of numbers. Matrices are classified by their dimensions, the number of rows by the number of columns. A matrix with m rows and n columns has dimension m by n. A square matrix has the same number of rows as it does columns. The dimension of a square matrix is n by n. And I know we've already went over this, but we need these definitions for what's coming up next. Associated with every square matrix is a real number called the determinant of A, denoted by det A or the A in the bars. Now normally you see it like this, but our book and my math lab chooses to use the det of A, which I'm just going to call determinant of A. The determinant of a 2 by 2 matrix A, where A is listed, is defined as the determinant of A equals the entry in row 1, column 1 times the entry in row 2, column 2 minus the entry in row 2, column 1 times the entry in row 1, column 2. Now I'm going to change this around just a little bit and switch the order of these. So what we're doing is we're multiplying these two minus, then we multiply the product of those two. Note, a matrix is a rectangular array of numbers, while a determinant is a single real number that is associated with that matrix. Find the determinant of A if A is equal to row 1, -3, 4, row 2, 6, 8. Well, the definition of a 2 by 2 matrix says you start up here and you do -3 times 8 minus, and then you start in this corner, 4 times 6, which would be -24 minus 24, which is -48. Now, if we wanted to do this on our calculator, we go back and enter our 2 by 2 matrix. So we go to second matrix. First thing we're going to do is edit and select A, which is already a 2 by 2 matrix. And then we just enter the values. -3, enter 4, enter 6, 8. Now remember, make sure after you enter the last entry that you press second quit. Now we want to find the determinant. So we're going to go back to our matrix menu, just like we did on the REF. We're going to go to Math, and if you'll notice, number 1 is the DET. We want to find the determinant of the matrix A, so now we have to go back to second matrix, choose option number 1, which was matrix A, and that would give us -48. Now this one's a little different. It says find X if the determinant of A is 6, and you have a 2 by 2 matrix with one of the values listed as X. Same thing. The determinant is 6, then you use the definition. 5 times 2 minus X times -3, which means 6 is equal to 10 plus 3X. Subtract 10 from both sides, and we get -4 equals 3X. Divide by 3, and we get -4/3. Now, Kramer's rule is another method of solving a system of linear equations using matrices and determinants. So what it says is you start out with 3 determinants. If there's 2 variables, we're going to have 3 determinants. We're going to have plain determinant D, which is simply the coefficients of the X column and the coefficients of the Y column. Then we're going to have the determinant with respect to X, which I'm just going to call dx. And if you'll notice, you've got the answers in the X column, and then your Y column stays B1, B2. And then we have our determinant with respect to Y, which we're going to call dy. And if you'll notice, the X column is there, and you have the answers in the Y column. Now, as a note, if D is equal to 0, Kramer's rule does not apply, and you'll have to solve it by a different method. So let's do an example. Use Kramer's rule to solve the system 5x plus 7y equals -1, and 6x plus 8y equals 1. Like I said, we're going to need 3 matrices. So D, remember, is our xy. dx, we're going to put the answers in the x, keep our y. And then dy, we're going to keep our x and put the answers in the y. So D would look like 5, 6, and 7, 8. dx, when you put your answers in the x column, would be -1, 1. Keep your y column, which would be 7, 8. dy, put your answers in the y column, which would be -1, 1. Keep your x column. Okay? So what we're going to do is do our little 2 by 2 formula. 5 times 8 minus 6 times 7. 40 minus 42. So our D would be -2. dx, doing the formula, would be -1 times 8 minus 7 times 1, which would be -8 minus 7, which is -15. And dy is equal to 5 times 1 minus -1 times 6, which is 5 plus 6, which would be 11. Now, I forgot to tell you on that earlier screen. Let me back up. Once you find D, dx, and dy, this is how you're actually going to solve the system. The way you find x is you divide dx by d, and the way you find y is by doing dy over d. So once we get our d, dx, and dy over on this problem, then we've got one more step. We have to say, well, x is dx over d, which would be -15 over -2, which is 15 over 2, which is 7.5. The y value would be dy over d, which is 11 over -2, which would be -5.5. So the solution to this system would be x is 7.5 and y would be -5.5. I'm going to run through another one real quick. We've got D, which is the x and the y, which is 3, 2, 2, -1. We've got dx, which we put our answers in the x column, keep our y column, 2, -1, and put our dy, we put our answers in the y column, -4, -5, and we keep our x values 3, 2. So D would be -3 minus 4, which is -7. dx would be 4 minus -10, which is 4 plus a +10, which is 14. And dy would be -15 minus, because the formula says minus, and -8 is -7. Now, one more step. X is dx over d, which would be 14 over -7, which is -2. And y would be dy over d, which would be -7 over -7, which is 1. Now, I'll tell you, I know this looks bad, but the neat thing about this method is you never have to deal with fractions until maybe the very, very, very last step. Now, extend this ideal of determinants to larger than 2 by 2 matrices. We're going to discuss 2 different ways to calculate a 3 by 3 determinant. Now, method 1 is relatively easy to calculate but it only works for 3 by 3 determinants. Method 2 is based on expansion by minors. You break everything down to 2 by 2 determinants, but this one can be used to calculate any size determinant. Method 1 says the determinant of a 3 by 3 matrix A, where A is listed below, is defined as the determinant of A equals, and I'll let you read that, and I know you're probably thinking there's no way that you're going to memorize that, but if you'll look, A11, A22, A33, that's these right here. And we'll go through in a minute and talk about the easier way to remember this formula. So what it says is, based on the formula, you rewrite the first 2 columns so that you get 5 columns. And then what you're going to do, let me switch over to a highlighter for a minute. Okay, so what you're going to do is you're going to go this diagonal plus this diagonal plus this diagonal. Then when you run out, you're going to come back up here and you're going to say minus this diagonal minus this diagonal minus this diagonal. Okay, I hope you could see that color. But anyway, what we're going to do is we always start up, okay, you always start up in this top left-hand corner. So you're going to go this way plus this way plus this way minus this way minus this way minus this way. Okay, are you ready? Starting there, we get 3 times 2 times 6 plus, that was this row. Then we're going to go this one. 1 times 4 times 0 plus. Then we're going to do this one. 0 times negative 1 times 2. Now you notice we're out of entries over here, so then we start back up here. Minus going back. We add going over, subtract going back. Then we're going to start here, and we've got this one. 1 times negative 1 times 6. Minus. Then you pick up this one. 3 times 4 times 2. Minus. Then you do this one. 0 times 2 times 0. Okay, now let's go through and get a number. 3 times 2 is 6 times 6 is 36. 1 times 4 times 0 is 0. 0 times negative 1 times 2 is 0. Minus 1 times negative 1 times 6 is negative 6. Minus 3 times 4 is 12 times 2 is 24. Minus 0. So simplifying that, we get 36 minus a negative 6 is plus a positive 6. Minus 24 would give us 42 minus 24, which is 18. Okay, so that one's pretty straightforward. Method 2, a couple of definitions. The minor is the value of the determinant of the smaller 2 by 2 matrix formed when you remove the row and the column of a specific entry. The specific entry's location in the matrix determines its sign. See the array of signs below? It always starts in a plus, and then everything alternates. Plus, minus, plus, plus, minus, plus, minus, plus, minus. Everything alternates. When you multiply the specific entry by its minor, you get the cofactor. Okay, and that probably makes no sense right now, but let's try one. Method 2, what you've got to be able to do is find the cofactor of 3. Well, what you do is you go through and you say, okay, this is a plus, minus, plus, minus, plus, minus, plus, minus, plus. Now, that doesn't affect the number at all. That's just going to determine, that's how the location of the number determines its sign. Now, to find the cofactor of 3, what you do is you remove the row and the column that contain the 3. Now, do you see that little 2 by 2 determinant left? Now, this 3 was in a positive spot, so we keep the sign of 3. And then we're going to do the determinant of 3 add the minor of 3. So that would be 2, 4, 2, 6. We only use that sign that we wrote up there out front. So we've got 3 times 2 times 6 is 12, minus 4 times 2 is 8. So we get 3 times 4, which is 12. Okay, so the cofactor of 3 is 12. Now, the cofactor of 1, that means we're looking at this number. So we're going to remove the row and the column of that. Now, because that 1 was in the minus spot, that would be negative 1 times the minor of 1. Well, if you remove the row and the column, we get negative 1, 0 in the first column, 4, 6 in the second column. So we get negative 1 times negative 6 minus 0, which is negative 1 times negative 6, which is 6. Okay? Find the cofactor of 0. Well, same thing. Let's remove our lines. This time we're looking at this 0. And I'm saying that because I said consider row 1, so we're sort of expanding on this row 1. So we've got 0 times, now plus minus plus, 0 is the same sign, the minor of 0, which means take out the row and the column that had 0. So that's negative 1, 0, 2, and 2, which is 0 times negative 2 minus 0, which is 0 times negative 2, which is 0. Technically, we didn't even have to do that because we knew 0 times anything was 0. So, now let's think about the steps for method 2. Choose any row or any column. Find the minor for each element in that row or column, just like we did on the other side. Use the array of the signs to determine the sign of the minor. Multiply that cofactor by the element in each row or column that you chose. Add or subtract these values to get the determinant. So if we went back over here, if I would have said choose row 1, then I would do 3 times the minor of that, which is 12, plus negative 1 times the minor of that 1, which was 6, plus 0 times the minor of that 0, which is 0, and we get 18, exactly what we got when we did it method 1. Okay, now this is the same determinant, but it says evaluate the determinant by expanding along the second column. This method, we can pick whichever row or whichever column we want. So if we're expanding along the second column, so we're thinking plus, minus, plus, minus. Okay, so what we're going to have is negative 1 times the minor of that negative 1 plus 2 times the minor of 2 minus 2 times the minor of that last 2. Okay, so that's how we get our setup. But you always start with that sign, and then this sign of an array of signs, you always start with a plus, and then this array of signs will help us out whether we're supposed to add or subtract that next term. So if we're expanding along this second column, we're going to mark out the row and the column that contained 1. So we get negative 1, 0, 4, 6, which would give us negative 6 minus 0. So negative 1 times negative 6, which is 6. Then we're going to expand on this 2. So we're going to mark out the row and the column that 2 was in, which leaves us 3, 0, 0, 6, which would be 2 times 18 minus 0, which would be 2 times 18, which is plus 36. Then we're going to do the last 2. We're going to mark out the row and the column that contain that 2. We get 3, negative 1, 0, and 4. So that's negative 2 times 12 minus 0, which would be minus 24. 6 plus 36 is 42. Minus 24 is 18. The point being, it really doesn't matter which row or which column you expand upon, you're going to get the same answer. Now, do you see the benefit in choosing either row 3 or column 3? Well, if you choose row 3, 0 times that minor, it's just going to be 0, so you really only have to calculate 2. Same thing on column 3. 0 times anything is 0, so you really only have to calculate 2 if you choose one of those rows or columns. Now, are you ready for the calculator? Later, we enter it just like we have been. Second matrix, we want to edit. This is a 3 by 3 matrix. Then we enter going straight across. 3, enter 1, enter 0, enter. -1, enter 2, enter 4, enter. 0, 2, 6, enter. And then we have to second quit. So we've stored our values into matrix A. Now we're going to go second matrix. We're going to slide the math. Option number 1 is determinant. Second matrix, because we stored all of our values in matrix A, we'll select matrix A. And that says that the determinant is 18. Now, how can Kramer's rule be extended to solve systems of equation with more than 2 equations and 2 variables? Well, if there's 3 equations and 3 variables, then instead of having 2 by 2 determinants, we're going to have 3 by 3 determinants. And remember, if D is 0, then Kramer's rule won't work. So what we would have is we would have D as being the X column, the Y column, and the Z column. dx, we move our answers in the X column, keep our Y columns and our Z columns. dy, we're going to put the answers in the Y column, so we'll have an X column and a Z column. And then dz, we're going to move our answers in the Z column, so we'll have an X column, a Y column, and a Z column. So once we get d, dx, dy, and dz, to find x, we simply do dx over d. To find y, we do dy over d. And then to find z, we do dz over d. So the first thing we're going to do is set up our determinants. D is 5, 2, 4 for the x's, 2, -1, 3 for the y's. That should be a z right there. 1, 1, 2 for the z's. dx would be answers in the x column. 15, 9, 13. Y's would be 2, -1, 3. Z's would be 1, 1, 2. dy would be keep your x columns, put your answers in the y column, and keep your z column. dz would be keep your x column, keep your y column, and move your answers into the z column. Everybody good? Now, from here, it's up to you on how you would like to solve each 3 by 3 determinant. I like the method 1 that says rewrite the first 2 columns so that you get 5 columns, and then multiply the diagonals. So for that first one, we would get 5 times -1 times 2, which is -10, plus 2 times 1 times 4 is 8, plus 1 times 2 times 3 is 6, minus 2 times 2 times 2, now I'm working backwards, 2 times 2 times 2 is 8, minus 5 times 1 times 3 is 15, minus 1 times negative 1 times 4, which would be negative 4, which would be negative 2. Negative 2 plus 6 is 4. 4 minus 8 is negative 4. Negative 4 minus 15 is negative 19. Negative 19 plus a positive 4 would be negative 15. You always want to check that first, because if d equals 0, we're through. We can't do anything. dx. Now, doing dx, dy, and dz the same way, I got dx is negative 45, dy is 15, and dz is negative 30. Okay, so once we find those values, x is dx over d, which would be negative 45 divided by negative 15, so x is 3. Y is dy over d, which is 15 over negative 15, which is negative 1. And z is dz over d, which would be negative 30 over negative 15, so d is 2. So we say that our solution would be 3, negative 1, and 2. Now, do you see how this method could be extended to evaluate 4 by 4 or larger? What you would do if you had a 4 by 4, and now we're getting real ugly, is you would go through and you would pick a row or a column. I'd probably be tempted to pick column 4. So we go back and do plus, minus, plus, minus, plus, minus, plus. So what we would have is we'd have negative 6 times that minor of 6, which would be a 3 by 3 determinant, plus 0 times the minor of it, minus 0 times the minor of it, plus 2 times the minor of 2, which is also going to be a 3 by 3 determinant. So anyway, because those are 0, that worked out well. We didn't have to have them, but that's how you could do a larger than 3 by 3 determinant. Now, what about solving systems of equations with 4 or more variables? You would set up your determinant based on your x column, y column, z column, q column, whatever. Then you would take that 4 by 4 determinant and do your dx, your dy, your dz, and your dq, whatever it is that you've got, and go about it that route. Okay, now you're ready to complete this section of homework on My Math Lab.